All right, let's all refocus. What are y'all working on? Is everybody working on the labs?
Yeah.
Shame on y'all. Shame on y'all. So I'll let y'all keep working on the labs, but make sure that you're paying attention also, because today we're talking about weather and atmospheric processes, and I'm going to try. I know I say this all the time. I'm going to try to get through this pretty quickly. So their case study or example that they use for severe weather, me and my wife actually lived through this one. So this one kind of hits personally for me. We were living in Norman, Oklahoma when this 2013 tornado hit, and it was insane. I was actually out of town at the time, and my wife was there. She got stuck at work because the tornado went over the highway that she used to get home. And literally the entire highway was shut down, and there's no way to get home. And so she had to sit at work for hours and take like a 3-hour trip home because the highway was shut down. It was a nightmare. We saw cars on the side of the highway like weeks later that looked like they come straight out of a war zone. Like, it was crazy. Twisted metal. A lot of people died in the 2013 one, more than I would have thought. So like in the 1999 one, 36 people died, 295 were injured, and it was a huge tornado, the highest ever recorded wind speeds, 484 kilometers per hour, which is about 300 miles per hour, and it destroyed about 10,000 homes. The 2013 tornado that hit almost the exact same place. Literally like the same stretch of land got hit by both tornadoes, like maybe 5 years apart. And so it was pretty crazy. So the 2013 tornado of comparable destructiveness followed remarkably similar paths. And then I think they go away from this and they'll talk about it towards the end. But living through this one, there were a lot of really sad stories. And I will say, I believe after the 1999 tornado, and we'll talk about this later in mitigation stuff, but I believe after the 1999 tornado, it was so bad, they passed a statewide law that all homes must have a tornado shelter. And so if you build a new home, it has to include a tornado shelter. For existing homes, I don't remember the exact law, but there was a like incentive for existing homes to get your tornado shelter. And if you did a certain amount of work of improvement on your home, they were like, hey, you should just go ahead and put in a tornado shelter. And for low income families that could not afford it, they had a program to try to offset the cost of that. Because I never experienced that because we have a lot of tornadoes in Texas. And they report on them kind of like normal tornadoes. With this tornado, when it was coming, the weatherman literally told you, he was like, you need to get out of your house and get into your car and leave. He's like, if you don't have a tornado shelter, your bathtub is not going to save you. Under the stairs is not going to save you. Like, you need to get out and leave now. And there were people who kind of saved themselves doing that. I think there was one story I remember. A dad went and picked up his daughter from school. He saw it on the news, sped to the school, picked up his daughter, and literally just drove out of town. And I think kids died at that school that day, which was pretty sad. But it was weird seeing the difference between Texas news reporters, and no offense to our local news reporters, if you all happen to be like related to them or really like them or something. Oklahoma weather people, like a whole level of professionalism above Texas weather people. I don't know why. Maybe it's that the University of Oklahoma has like a really crazy weather program, so a lot of local grads stay around there. But they will cut in for a full day of weather. They're not cutting back out to like let you watch the end of the baseball game or Wheel of Fortune or something. They're like weather 24 hours a day if it's a crazy weather day. So I remember this one pretty in depth as far as the 2013 tornado. So yeah, you can see there's no part of your home that you're hiding in and surviving this tornado. You're either underground or you're not there or you're having a really, really bad day. And it was like this for miles and miles and miles. It was insane. You couldn't even see the roads afterwards when you saw helicopters flying overhead. You couldn't see where the streets were. Just crazy, the craziest thing you've ever seen. So then they get into energy. And we're going to talk about weather. So when we're talking about weather, ultimately we're talking about sunlight. Where our weather gets its energy is from sunlight, where the sunlight goes, where I have areas of heated up material versus cold material. And that mixing between hot and cold air is what's going to give us our weather. So they're starting off with energy, which they talk about force, work, and power, which is a little bit more physics stuff, but it does apply here. The reason they're mentioning these is because of the energy we get from the sun. So as that sun energy comes in and heats up part of the atmosphere, we're looking for these things to kind of take effect in our weather. So they talk about the different types of energy: potential energy, kinetic energy, and heat energy, which all kind of stand for themselves. Potential energy is stored, kinetic energy is in motion, and heat energy is technically a type of kinetic energy because anything that's hot also is moving very quickly as far as the atoms are concerned. So somewhat similar there, but we're good. So latent heat, we talked about latent heat in chemistry. This is the idea that it takes energy to actually switch from one phase to another. So like if I'm boiling water, obviously when I'm boiling the water, I'm putting energy in and the temperature's coming up. But once the water starts to boil, if you have a thermometer in, you will see the temperature like level out. And basically that leveling out is now the energy that I'm putting into the water isn't going to raising the temperature. It's actually going to converting that water from liquid to a gas. And so the temperature kind of levels out until almost all of the water is boiled off into gas. And then it can start to rise again and you can heat your steam up even more. But that level where the temperature doesn't really change, but I'm still putting in energy, that is called latent heat. That latent heat is the energy required to change phases. And what you see is your temperature kind of levels out during the latent heat phase because the energy isn't going to temperature change, it's going to phase change. So they talk about the three ways we transfer heat: conduction, convection, radiation. Just remember, hopefully from chemistry, conduction is when I'm touching something. So you have to have physical contact in order for conduction to happen. But yeah, if you have hot hands, I never knew I had this. You find out a lot of things about yourself when you're with like a long-term partner. But apparently I have like blazing hot hands. So after we dinner, when my wife will grab my spoon or my plate, she'll be like, "Oh my God, your spoon is so hot." And she lets me feel my spoon compared to her spoon. And her spoon's like cold and my spoon is like warm. Yesterday she said, we were like having a little conversation and I was standing like with my hand on the doorknob. And she's like, the side of the door where your hand was is so much hotter than the other side of the door. It's crazy. So yeah, apparently I have hot hands, and you feel that through conduction because anything I touch starts to turn hotter. Convection is, as you know, hot things rising, cold things sinking. So think of like hot coffee in a coffee mug circulating around, or hot air rising in a house. Does anybody have a second story home? The second story is always hotter than the upper story. Unless you have like amazing air conditioning, it's always hotter because the hot air rises and the cold air sinks. And then radiation. Radiation is when you feel heat that's not through conduction or convection. It's the actual passage of electromagnetic radiation waves. So like when you're sitting next to a campfire and the wind's blowing away from you, so you're not getting any smoke, but you feel that heat, that is radiation coming off of the embers of the campfire. And so conduction, convection, radiation are the three ways that we transfer heat. Here's a great example of that. Convection happens in the boiling pan. Conduction happens when the pan is actually on the burner or between your hand and the handle. And then radiation is going to be you feeling the heat from that burner, even though you're not directly over it. It is radiating heat outwards towards you. So the Earth's energy balance. When we talk about weather, we have to talk about where we're getting our energy from and where it's going to. And so basically the way we do this, we think of the sun's energy as basically all of our energy. Yes, the inside of the Earth, my globe was over here, but now it's back there. Yes, the inside of the Earth is hot, and there's things like lava and magma in there. But in general, that heat doesn't really contribute in a significant way to our surface atmosphere or heat that we feel on an everyday basis. So what does almost 100% is the sun's energy. So when we talk about weather and energy of the atmosphere, we're going to be dividing up where the sun's energy goes. So it drives the hydrologic cycle, the ocean waves and currents, and the global atmosphere circulation. So basically everything that has to do with weather comes from the sun's energy. And nearly all of the energy available at the Earth's surface comes from the sun. We're not really getting energy from the Earth itself. Most of the sun's energy is electromagnetic, so that's your radiation that you're getting. Described by the wavelength, the distance from one crest to another. All wavelengths are parts of the electromagnetic spectrum. Only a small part of this is visible to us, but we can still enjoy the heat of the rest of the part. So they show us here incoming shortwave radiation from the sun. So all of this is what we get from the sun. The stuff in the rainbow section is the part that we can actually see. That's part of the visible spectrum for us. But we do get a decent amount of ultraviolet rays, probably some X-rays. You get a little bit of infrared, you get a little bit of microwaves, TV, radio waves. Just depends on what part of the spectrum you're looking at. And really, what type of atmosphere it's coming through can block quite a bit of this. Once electromagnetic energy from the sun reaches the Earth, it is, so once it gets to us, the energy from the sun can either do one of three things. It's either going to be redirected to a different place, it's going to be transmitted through the atmosphere and actually get to the Earth, or it's going to be absorbed into the atmosphere or molecules in the atmosphere. So redirection is bouncing back to space by clouds, water, or land. Or scattering can disperse energy in many directions. Transmitted is where it gets through. It's passed through the atmosphere. It probably hits something on the surface or the surface itself. Or absorbed means it's going to be absorbed by the atmosphere or clouds or some sort of molecules, and it's going to help to heat up the atmosphere. So they talk about reflection. Reflection depends on albedo, and this is a new term. Albedo, your number of albedo describes how good you are at reflecting things. And usually this is used to describe natural stuff. Obviously, man-made things are very good at reflecting light. But natural stuff, we want to know how much light is being reflected, how much is being absorbed. So their example here, a dark woodlands. Obviously, woods are going to be really good at absorbing light. That's like their entire thing that they do. They're nice and dark. And at the bottom of the woods, you have a essential shadow, right? At the floor of the forest, it's usually pretty dark because the trees are pretty good at absorbing all the light. So those trees aren't going to reflect a lot of light. Their albedo is like 5 to 15%, relatively low. If you get to light grasslands, the grass is still good at absorbing light, but it's a lighter color. And so it's going to reflect some back. It's going to be like 25%. If you're on a beach with no grass and it's just like a light colored sand, you could get a lot of reflection and it could be up near like 50% or higher. Has anybody noticed this is not new news or anything, but you got to wear sunglasses at the beach, not just to look cool, because the sand and the water is really bright. And that's just because they have a high albedo. They actually reflect a lot of light back at you. Absorption. Energy that is not reflected is absorbed. Different objects absorb different wavelengths, and hotter objects radiate energy more rapidly at shorter wavelengths. And so depending on what your material is, it's going to absorb that sunlight. We can go back to the beach, or we can talk about roads. We've all walked out onto a hot surface. If you walk barefooted out onto the road, and it's one of those dark roads here in Texas, it just absorbs all that energy and will radiate it back outwards at you, so you can feel how hot the road is. Same thing with beach sand. It's just absorbing that sun, and as soon as you step on it, you can feel how hot it actually is. So here's a general albedo or energy budget. And so what they're showing is 100% of our incoming solar radiation. So the sun that actually hits the earth, we're just going to say that's 100% of our energy. Of that, 25% gets absorbed by the atmosphere. So 25% of that 100% will never actually reach the ground. It's used to heat up the atmosphere and the clouds and the water in the clouds. 45%, so less than half, will actually make it to the Earth's surface. So if it weren't for our atmosphere and the different things that reflect the sun's energy, it would actually be a lot hotter here on Earth for our position with the sun. We're only getting about 45% of that energy right now. If we were to get 100%, it would probably be very difficult for us to live our normal lives here. And then 30% gets reflected back to space, 25% from the atmosphere, and about 5% from the surface of the Earth. We do have quite a bit of water on the Earth, and water reflects light actually very well. And so the Earth itself is reflecting some of this energy back. So that adds up to 100% of the total outgoing infrared radiation, along with the heat that the Earth is actually giving off. So the heat from the Earth itself, being a warm body, is slowly radiating out to space. And notice, of the 100% of sun energy coming in, 30% never gets here. It automatically goes back out. And then we have another percentage, which doesn't really these percentages don't really equate to this percent. But we have another amount of energy that the Earth just naturally loses. And so I'm not an alarmist or anything, and I'm not telling you all that you need to prepare for the upcoming apocalypse. But when you see the budget that we have here and just how much energy we're talking about and how much energy we really don't get from the sun, when you hear scientists talk about greenhouse gases and climate change and the way that they worry about temperature rising, you can see here that this budget is very delicate. And if you start to trap more heat that normally leaves the Earth through this process, or if you're not reflecting as much heat, you can really change this budget and things can get bad or out of hand very quickly. So it's something to keep your mind on, or kind of think about, that we operate on less than half of the sun's possible energy. And if we're not allowed to get rid of that energy somewhere, we could all just kind of cook here on the Earth and get a lot hotter. So let's see. Now we're going to talk about the atmosphere. The atmosphere is a thin gas envelope that surrounds the Earth, causes weather experienced every day. It's responsible for trapping heat that keeps the Earth warm. Here's a nice picture of our atmosphere. That's why the sky is blue. It's why the Texas sunsets are amazing. Oh, by the way, I don't know if any of y'all ever plan on moving out of Texas. I've heard that Texas has one of the best sunsets in the country, and that there's not really a lot of other places that get great sunsets like Texas. So enjoy a sunset and a sunrise every once in a while, because maybe in a place where you go, you don't get to see it too often. I think one of the things that contributes to that is that we're really flat, and so you can see the sunset and sunrise all the way down to the horizon, which is nice. Let's see. Our atmosphere, mostly nitrogen and oxygen. It's like 70%, 71% nitrogen and close to 30% oxygen. It's mostly nitrogen and oxygen with just a little bit of all sorts of other stuff in it. There's quite a bit of water in the atmosphere. It's important for cloud formation and circulation. It comes from evaporation of water on the Earth's surface. And we use humidity to describe how much moisture is in a particular piece of air. Then they go into the structure of the atmosphere, which we went through last year. Troposphere is going to be your lower layer. I remember that because it reminds me of the word tropical, and all the tropical stuff happens at the Earth's surface. This is probably not a good reminder, but that's how I think of it. So troposphere is at the Earth's surface. It's the layer that we live in. Pretty much all of the Earth's surface is in the troposphere. It's also where a lot of our weather happens. Most visible characteristics is the presence of our clouds, cumulonimbus clouds. Here's a nice image of all your different layers. So we start at the bottom with the troposphere. This has everything on the surface, including most of our weather. If you go up to the stratosphere is where planes fly. It's also where our maximum ozone layer is. So this is the ozone layer that protects us. You go up from stratosphere into mesosphere. This is where you will see shooting stars burn up. I forget what else happens in the mesosphere. And then you go up even higher and you get into the thermosphere, which is where you see northern lights if you're in the right part of the world to see northern lights. And then even higher would be the exosphere, which is the arguable boundary between our atmosphere and space. There really is no like edge of space or our atmosphere, and so you can always argue whether you're still in the atmosphere or not. It's an interesting thing. You can't really draw a line there. So one of the things I'd like to point out as we go up through these different layers, look at how the temperature changes. We're all familiar with the troposphere. As we go up higher in elevations, it gets colder, right? So if you go up a mountain, there's ice and snow at the top of the mountain because the temperature is much colder, and that's because we're going up in the atmosphere. So we're all pretty familiar with that. The higher up you go, the colder it should get. But the truth is, as you go up higher, it actually doesn't continue to get colder forever. It will get warmer throughout the stratosphere. So as you come up through the ozone layer and get higher and higher in the stratosphere, you're warming back up, almost back to regular ground level temperatures. Then in the mesosphere, you cool back down. So we got that cooling effect happening through the mesosphere. And then thermosphere, thermo means heat, so you could guess that we're going to heat back up in the thermosphere, and we do. Our temperature rises and rises and rises as we move up to the thermosphere. And then once you get to space, it's going to start to fall again because space is going to be cold. So cloud types associated with severe weather, pretty much just the cumulonimbus. This is going to be your severe weather cloud. The rest of these down here can have some rain, but in general, not very much. So your stratocumulus can be your little tiny rain showers. Anything that has that vertical development, like it's the big tall clouds, those are going to be your thunderstorm type clouds. So cumulonimbus is the big one. That's the big anvil shaped head. They talk about these in the news all the time, and these are the ones that can spin off your severe weather and your tornadoes in the right circumstances. So 4 aspects of weather directly related to severe weather. What is the atmospheric pressure and the circulation patterns? Notice that's number 1. It's all about how much pressure you have, and the pressure is really going to show your relation between your 2 different air packages. If I have a really hot air package and a cold air package, I'm going to have a huge pressure difference there. That's going to relate to some severe weather. Vertical stability of the atmosphere, more importantly, instability. Vertical instability of the atmosphere is going to affect your severe weather. It allows your air packages to rise and form that severe weather. Coriolis effect, this is going to be for rotational storms. So if you're looking at possible tornado effects or hurricane effects, that's your Coriolis effect that's going to take place. And then interactions with different air masses. How are the 2 different air packages interacting? You have to have this interaction to have severe weather. You will not have severe weather just in the middle of a huge state that only has warm air. You have to have cold air and warm air mixing somewhere in order to have severe weather. So atmospheric processes are also called barometric pressure because we're really looking at the pressure here. Barometric pressure, a weight of a column of air above a given point. So literally, we weigh the air above us. We're weighing the atmosphere and figuring out how much pressure is there. And the atmosphere pressure decreases with increasing altitude. Nearly all of the weight of the atmosphere is in the lower atmospheres down in the troposphere. Density and pressure decrease rapidly as you go higher and higher in elevations, which is why your temperature also decreases. They're just showing you the atmosphere here. Up in the upper parts of the atmosphere, it's very, very spread out and less dense. Down in the lower parts of the atmosphere where we live and breathe, there's air all around us, and it's always getting us and keeping us alive. Let's keep going. Changes in air temperature and in movement are responsible for horizontal changes in pressure. At the equator, air is warm and low in density. Okay, so they're just setting up the convection cycles here. At the equator, you get the most sun. It's heating up your air. And so what your air going to do, it's going to rise up in the atmosphere because hot things rise in a convection cell. As it rises up in the atmosphere, something else has to go down. So cold air from the top of the atmosphere is going to come down, and you're going to start these convection cycles that run pretty much 24/7, 365 around the world. When our weather pattern changes, it's just because those convection cycles shift a little bit. And you can see the same convection cycles here inside a single cloud. And so you have inside the anvil cloud, air is rising up. As it rises up, it's losing its pressure, it's cooling down, it's going to drop all of its rain, which is what creates your severe weather there. So they're talking about global currents and weather patterns. And so they talk about jet streams, which are mid-altitude air masses of different temperatures colliding near tropopause. The northern hemisphere has two jet streams, the polar jet stream and the subtropical jet stream. And so they're showing you those here. This polar jet stream is one that brings us our winter weather. And so you can, if you watch the weather frequently, you can see that most of the time, unless it's a really rare situation, the weather is moving from west to east. That's almost always how it happens, west to east. Every once in a while, we'll get a warm air package up from the Gulf, but usually like 2 days before the weather hits here in Texas, they watch it come over California. And so that's how they're keeping track of these things. So these jet streams and where they're at and how they go greatly affects our weather. If they're ever talking about El Nino or La Nina and why our weather is so weird during the winter or summer, it's because of this subtropical jet stream and which direction it's moving. Air movement can cause changes in air pressure. Obviously, when two different air packages converge and push together, that's going to bring my pressure up. It's going to increase my pressure. When two air packages are splitting apart and kind of leaving a hole, that's going to decrease the air pressure. At the surface, air moves from surface high pressures to low pressures. And that makes sense. Where the pressure's high, the air is going to leave. Where the pressure's low, it's going to go. It's just like having air in a balloon and letting it out. When I blow air into the balloon, I'm creating high pressure. When I let go of the balloon, the high pressure is going to try to leave and go to the low pressure area. So they're just showing you your interactions between your highs and lows. Notice air is moving away from the high pressure zone at the surface and moving into the low pressure zone at the surface. And so that's what we expect to be happening with all of our pressure. And then as these two swirl and interact, that's where you're going to get your weather generally, usually around the low pressure system. So now they're going through a couple fronts. This is going to be a cold front. This is where your cold air is moving in. The hot air is going to rise above it. As it rises, it's going to cool down. It's going to lose its water, and everything's going to rain out, and it's going to form your big storm clouds and thunder clouds. Here is a warm front moving in. The warm front's going to push over the cold front more slowly. You're going to get clouds, but not really dangerous weather. No thunderstorms or big cumulonimbus clouds, just a general stretching out of like a cloudy day. Here's a nice weather map. We did a little weather at the end of last semester, right? Is that right? Yeah. We did the weather map and everything. And so this is just showing, well, I know that y'all weren't here, but this is just showing a little bit of the kind of things you'll see on a weather map. So you have a warm front right here in red. You've got a cold front over here. The alternating red and blue is going to be a stationary front. It's just kind of sitting there. And then over here in the purple, we have an occluded front. That's when a faster moving cold front catches up with a warm front. So they just combine the red and the blue to make a purple, which is nice. What else do we have? Unstable air. So it says the tendency of air is to remain in place. If your atmosphere is stable and all your air is remaining in the same place, you're not going to have weather, or at least not interesting weather. It's just going to be a normal day. So the hot days in summer, when the wind isn't blowing and there's no rain and it won't rain for like another month, that's because our air is just really stable. There's no new air packages coming in. There's nothing really moving. It's all just sitting here. When you get unstable air, that's when the interesting stuff happens. Parcels or packets of your air are rising until they reach air of similar temperature and density. Everything starts to mix. You get what we call instability, and you start to form weather clouds or weather fronts. A front is a boundary between cooler and warmer air. The fronts are going to be based on which air is moving. So a warm front, the warm air is moving into the cold air. A cold front, the cold air is moving into the warm air. So the fronts are named after which air package is actually moving into the other one. A stationary front, neither one's moving. They're just sitting side by side. And so that's where we drew the line that was blue and red, alternating back and forth. This was their stationary front. So it's alternating back and forth, pointing in different directions. So there's a warm air package here and a cold air package here, and they're just kind of sitting there, not moving at all. Let's see. Severe weather refers to all sorts of things. It could be thunderstorms. It could be tornadoes. So these are for our Texans. Hurricanes, maybe for southern Texans or deep south people. Blizzards and ice storms for our northern brethren. Mountain windstorms for the mountain folk. Heat waves for our desert friends. Or Texans, I guess we get heat waves too. And dust storms. I have a family that live in Arizona, and my cousin always sends me pictures of haboobs, which are giant like dust storms that blow in over the town, and it's crazy. It's just like a giant wall of dust that covers out the entire sky. It's called haboobs, like H. No. Like, we know what a kazoo is, Mr. Bailey. You don't have to lie to us. But yeah, it's like the crazy like dust storm that like you'd see in a movie or something, but it's just in Arizona. It's just right there. So let's see. So, all right, we went through all these. Hazardous due to the energy they release and the damage they are capable of causing. Most occur in equatorial regions. They're talking about thunderstorms. Most common in the afternoon or evening hours in spring or summer. I will say, after you live here a while, you notice that most of the storms that come in through Texas happen overnight. Very rarely do we get like severe weather like at noon in the middle of a day. I don't know why, but something about it. 3 conditions necessary for thunderstorms. You have to have your warm and humid air available in the lower atmosphere. A steep vertical temperature gradient, such as the rising air, is warmer than the air above it. And then a colder air over your warm, moist air. And then the final thing, updraft must force that warm air up into the atmosphere. So I got to have warm air at the surface. I got to have cold air above it. And then I need to force that warm air upwards. That's how you make a thunderstorm. That's how you get it going. Days with thunderstorms. Notice Texas is in the high range area. So on average, every year, out of 365 days, we have roughly 50 of them having thunderstorms in them. So that's fairly high for the country. Only really Florida is higher with 80 to 100. I will say, I don't know. I haven't like lived in Florida, but I've been to Florida once, and I'm not questioning whether they have more storms than us. The storms that I encountered in Florida were very quick. Like, they happened and then they went away, and like the day was nice, and you just still went to the beach and everything. It wasn't like in Texas where it just kind of messes up your entire day sometimes. But I didn't live there. I don't know. Maybe a Florida person's like, you shut up. We got bad storms. Leave us alone. Thunderstorms. So stages of your thunderstorms. How do they develop? So you start with your cumulus stage where it's just a standard cloud. Obviously, it's going to have to grow. You're going to have to get the conditions right for your cloud to progress. But how much time do we have left? Am I going to finish this thing? 27. We're good. I can do it. Then it's going to mature. It's going to get bigger. You're going to have downdrafts and falling precipitation leave the base of the cloud. Your rain starts to happen. More importantly, you get updrafts and downdrafts. So I need air being pushed up to form more rain to cool down the warm air at the bottom. And I need cold air being pushed down. I need that circulation in the cloud. Once I get that circulation, my cloud really starts to grow, starts to produce a lot of heavy rain. Until I get to the dissipation stage. The dissipation stage is where I start to run out of energy. My updrafting and my downdrafting are going to start to subside a little bit. Upward supply of moist air is blocked by the downdrafts. My thunderstorm basically gets cut off from its fuel supply. It starts to weaken. Your rain starts to die off a little bit, and your cloud just breaks apart. And so here's your developing stage. I start off as a normal little cumulus cloud, but the updrafts are feeding me with more and more energy. Here's my mature stage. I'm still getting updrafts. They're feeding energy from that warm air into my storm, but I'm getting downdrafts, and this nice circulation is help keeping my cloud nice and robust and rainy. And then at the end, I lose my updrafts. So I've now cut off my storm from all fuel that was kind of driving it. I have nothing left but the rain going on, and so it's just going to deplete all its energy pretty quickly and dissipate out into the atmosphere. So now, thunderstorms continue. Air mass thunderstorms are most individual thunderstorms. They last less than an hour and do little damage. If I had to guess, this is probably what the majority of Florida thunderstorms are. Severe thunderstorms, if I also had to guess, this is probably, I don't know about the majority, but maybe close to half of what our thunderstorms are. We usually get the severe ones that come through. They in general have a chance of generating a tornado, even if they don't. So they can be classified as severe by the National Weather Service if the winds reach 58 miles per hour, or you get hailstones greater than 3/4 of an inch. Which we get sometimes. We don't get hailstones all that much. But I'd say 58-mile-an-hour winds in a thunderstorm probably aren't too uncommon here. Necessary conditions, large changes in vertical wind shear, high water vapor content in the lower atmosphere. Got to have that updraft that makes your air unstable. And then dry air mass above the moist air mass. When the moisture goes up, it's going to get squeezed out and create a lot of rain. Vertical wind shear. This is actually something interesting that happens in the atmosphere, and it's just something you should file away in your brain and keep for later. Know that the higher you get above the ground, the wind is not blowing in the same direction that you feel it down on the ground. And the reason for that is a combination of the Coriolis effect and friction. So the idea is when the wind is blowing across the ground here, it's getting friction from all the things on the ground. Whether it's grass isn't going to do a whole lot, but trees and buildings and hills and other things that kind of stick up from the surface of the earth are going to create friction with the wind, and that's going to be acted on by the Coriolis effect, which is going to kind of curve the wind off in a certain direction, depending on what hemisphere you're in. So you can see here, the wind is blowing this direction if I'm a person standing on the ground. But as I get higher and higher and higher in the atmosphere, it's going to its standard actual direction of the wind blowing, which, like, if I'm a pilot, I need to be aware of that. If I'm a person on the ground, it doesn't really affect me. It's not ever going to change anything. But it is something to be aware of, that the wind is blowing in different directions at different elevations above the Earth's surface. And stronger. That's kind of something we could all just guess. That at the surface of the earth, the wind's not that strong. The higher up I go, the wind is going to be very strong. If you've ever been to the top of a tall building, you probably experienced the wind blowing a lot harder than you remember it being on the ground. So severe thunderstorm types. There's been a lot of slides on thunderstorms. Squall lines. These are the ones like the straight line that just blows through. And it's like really heavy storm for like 30 minutes an hour, and then it's gone. But those are the ones where you see like literally the whole line of thunderstorms coming across the state. Supercells are your big thunderstorms. These are the ones that produce tornadoes around here. Large storm with a general rotation, but it's not really the rotation of the storm that causes the thunderstorms. It's small rotations on the edge of that overall cloud. So it is an upward spiraling column of air known as a mesocycle, but your small little tornadoes spawn off the side of that from different rotation patterns. So this is just showing you some of the rotational patterns that could happen in different storms and what can form here. They've got a little tornado spawned off the side of this one. Downbursts and thunderstorms. These can generate strong straight line winds. These don't happen anymore, but or not anymore. They don't happen super often, is what I was meaning to say. A microburst is what hit the Dallas Cowboys training facility, like, was that 5 or 10 years ago? It like knocked a building down and killed a trainer. It was pretty crazy. Like they were practicing in one of those like tent buildings, almost like a football field covered with a tent, so you can air condition it. And a microburst came out of like nowhere. I don't think it was even particularly stormy that day, and literally knocked the whole building down while they were practicing. And I believe one of the coaches or training assistants died. Pretty crazy. This is well before the star and all that. So lightning and thunderstorms, common occurrence during thunderstorms. Most of it is cloud to cloud. Cloud to ground is less common, but you do get 25 million ground strikes in the United States each year. Generally kills about 100 people and injures more than 300 each year in the United States. And if you're on the internet at all, you see videos, or I see videos all the time of people getting struck by lightning. So not that uncommon. So here's your cloud to ground lightning. Here's a little bit of cloud to cloud lightning off to the side. Development of cloud to ground lightning. You just have ions get built up in your cloud. If you get a bunch of positive or negative ions localized in a certain area, you get a charge built up, and they want to even that charge out, and so the lightning is going to perform that function. Hail. We're a little bit familiar with hail in Texas. You got to have that updraft. When the updraft pushes your water back up into the cold air in the cloud, it can freeze. It comes back down. Your updraft pushes it back up, and your hail just gets bigger and bigger and bigger until it overcomes the weight of the winds of the storm, because gravity's pulling it down, and it comes through your roof or your windshield. Hopefully it's not too big and you just get a couple dents and not anything bad. Now, tornadoes. God, there's so much stuff. I really thought I could get through this. Usually spawned by severe thunderstorms, one of nature's most violent natural processes. 1992 to 2002, so in that decade, killed an average of 62 people per year. And then they go through a couple of these. So we'll finish this up Monday. We'll finish this up Monday, because today's Friday. Yes, today's Friday. It's wonderful.
Good weekend.
Yes, just at further over on that corner there. There you go. Yeah. Thank you.